instead of just having point estimates for the population parameter, our goal will be to actually provide an interval, okay, with an associated confidence with that interval. Because when we have a single estimate, we cannot associate a confidence with it because it's a single point. Is it really the theta that you're is how confident you are that that is lambda? Lambda, probably your estimate is going to be different from the actual lambda with very high likelihood because it's if that lambda is something continuous, finding that exact lambda will be impossible from just a sample. For that, the confidence interval is the idea to enlarge your estimate to a region, to an interval, and by associating some confidence with it, which will say that this confidence is basically saying that you'll have some level. This confidence one minus alpha is called the confidence level. Alpha is going to be a small number here. For example, when alpha is the most widely used ones are 0.05. When alpha is equal to 0.05, it means that your confidence level is 0.95. With 0.95 confidence level, in other words, with 0.95 probability, the parameter is contained within this interval between A and B. So it's just an enlarged area instead of a single theta. It's an interval on your parameter space. So which will make sense, right? I mean, instead of just having something, you can have a confidence interval. And this confidence interval, as you can see, it's going to just not only contain theta, it also contains some information about the standard error of theta hat. Because when standard error is large, if your standard error is large, you cannot give small intervals. The interval, if the standard error you compute for theta hat is large, it's likely to, if you want to have the same confidence level, you have to increase your interval. And also, we don't want to have our interval to be from minus infinity to plus infinity, which will have 1.0 confidence level, but it will have not much meaning, right? I mean, we want the intervals as small as possible. At the same time, we want the confidence levels to be high, but these are two competitive competing features, properties. Decreasing the interval is going to decrease your confidence level for the same standard error. Either you have to find a way to decrease your standard error, and we already know that, right? For example, if it's a consistent estimator, increasing your sample size may decrease your standard error, hence it may decrease your size of the confidence interval. So this one, the confidence interval we are going to be building is going to be something like this. Let me get, and you're going to see techniques to build confidence intervals for different estimates like population mean, population difference between two population means. So if we have some theta hat here, we are going to, this is our point estimate, and we are going to add, this is called margin, the margin of an interval. So let me show it here. If this is your point estimate for your theta, we are going to be building an interval around this, and this one, is called the margin. Okay, so we are going to, if for example, if you want the margin to be smaller than some delta value, you are going to see that the way to do that is to increase your sample size. By increasing sample size, and this margin, we are going to see that you'll be able to compute this with this. Whatever the standard error of this is, this margin is going to be computed. It depends on a couple of things. For example, it first depends on alpha. What is your confidence level? And what is your standard error? Okay, so these are the two things. that margin uh, depends on. If you want large confidence level, uh, which means smaller alpha, large confidence means small alpha. If you decrease alpha, your margin is going to increase, which means that if you want to increase your confidence that this interval contains the actual theta, one way to do that is to increase the interval, right? Another thing is the standard error here. If you have a low standard error, the margin can decrease with low standard error. With low standard error, you can get a smaller margin. So basically, this is when we're building confidence interval for population means or different things, we're going to be uh, computing these things. And what is this alpha here? And how, this margin actually, as I said, it depends on alpha and the standard error of this thing. And we will actually, when we are building these confidence intervals, we will make use of the fact that these estimators are asymptotically normal. Asymptotically normal means that if you want, for example, let's actually, asymptotically normal means that you'll be able to standardize them. You will be able to look at the standard normal distribution table for a particular value of alpha, which will tell us how many standard errors you have to go to the left and to the right of your theta hat. So this based on this alpha, we are going to get ourselves a z value from the this standard normal table, which will tell us multiply this z with the standard error and go that much away from left and right of the margin. So the derivation of this is really critical because at first, if you understand that using this z to the left and to the right side of this, and theta is in this, so it's like theta seems to be at the center, but it's not theta here, it's theta hat. So how can we guarantee that theta hat, which we assume is coming from the same, actually we don't need to assume that it's coming from the same distribution, but we are going to, when we standardize this, let's assume if this theta hat, let's see how we can use this fact that theta hat is asymptotically normal to start building this confidence interval. Asymptotically normal means that its standardized form is standard normal distribution. What is its standard form? Its standard form is theta hat subtract from it the expected value of theta hat and divide the standard deviation. So if this is your random variable, theta hat is a random variable, right? If you remember, whatever our random variable is, if you subtract from it, if this is a normal random variable, if you subtract mu from it, okay, if this x is any normal variable, if you subtract mu and divide by standard deviation, you standardize it. This is the way we were standardizing, making standard normal. From if this x is a normal variable, if you move it mu units to the left and you divide this by standard deviation, this becomes a standard normal variable. Whatever x is, this will be a standard normal variable. So if theta hat is asymptotically normal, meaning that for large n, theta hat behaves like a normally distributed variable. This is what it means. Asymptotically normal means that for large n, theta hat is a normal variable. It may, but we are not saying it's standard normal. We're just saying it's a normal variable, normally distributed variable. So let me just then say that let's standardize it. When we standardize it, you subtract its expected value from it and divide by its standard error. Now, what do we have here? We have a term in our hand. Another thing we need to use here, can I write theta here instead of this? In order to write theta instead of this one, in addition to being asymptotically normal, my estimator need to have another property, right? What was that property? Exactly. Yes, exactly. Right on the point. It must be unbiased. So therefore, now we are seeing confidence the way in order if you want to build confidence intervals by using the techniques that are described in chapter section 9.2, your estimator has to have these properties. If you have an estimator which is unbiased and asymptotically normal, then we will be able to use the techniques that we see in this section 9.2. So actually those will be the algorithm for building confidence intervals will have first two steps. First, show that your estimator is unbiased. Then show that it's asymptotically normal. So, and since all the mean, average of means, proportions that we will estimate, they satisfy these properties. You don't need to do these checks in the exam or thing, but or anywhere. But if you have some estimator for something interesting that you're encountering the first time, in order to build confidence intervals properly by using the normal distribution table, for example, you have to show that it's unbiased and you have to show that it's asymptotically normal. Now this one, sorry, this one here, this is the standard error of our estimator. So this is the standard error, which is here in this term. And this is, look at this variable, theta minus theta hat minus theta. So we have an equation. This is a really important equation so this is theta hat. This is an important equation that have both our estimator and the thing that we're estimating in one equation. We will be making use of this to build our confidence intervals. Now, let's look at this variable. Theta hat minus theta divided by, okay, so what is this? What is the distribution of this equation that I write here? It's standard normal, right? Which means that it's centered at 0 with a standard deviation of 1. So I standardize this variable. So this equation that I write here, which is a random variable because theta hat is random, this is a standard normal variable. Now, here, what is the probability? Now let's look at, for example, now this is the place where we are going to have our alpha. We are going to bring alpha to this picture. All right. If you look at the probability that, for example, for an alpha of 0.05, look at this. The probability look at these two things. I'm going to have 2 points here, which I'm going to name as minus z alpha over 2 and z alpha over 2. Z alpha over 2. For example, if alpha is 0.05, this is going to be, so this is a very well-known value. I think it's 1.96 minus 1.96 and plus 1.96. So 95% of the population is here. So let's write this. So what it means is that the probability, so this is a standard random variable. The probability that minus z alpha over 2 is less than or equal to, or less than, doesn't matter, it's continuous, theta hat minus theta. So this is my standard variable, right? So this is my standard variable. The probability that it is between these two things is equal to what? 0. I mean, if alpha is equal to 0.5, it's going to be equal to 1 minus alpha, actually, whatever 1 minus alpha is. The probability is going to be equal to this 1 minus alpha. how I got this. So alpha, so the area alpha is going to be a number between 0 and 1. And what I did was just think about, so the area to the left of this one here is alpha minus 2, right? The area to the right of this is also alpha minus 2. So this is z alpha minus 2. So these were probabilities. So this z alpha minus z alpha over 2 means that actually this is not, it should be, yeah, right. So, so do I, yeah, exactly. So this is whatever this alpha here is, if this alpha, so the area under the curve to the right hand side is 0 0.25, 0 0.020, 0 0.025. The area to the left hand side is 0 0.025. So what is the area under the curve here? It's 1 minus alpha, right? So the probability that our standard random variable, which is this, the probability that it is between these two things is going to be 1 minus alpha, which is 0.95 here. Now, here, what we're going to do is, so we have an equation at our hand, which contains the standard deviation, our standard random variable, and these z alpha minus z alpha over 2 z and 1 minus alpha. So what we are going to do is, in order to have this probability, we can also take this theta out. So we want to say that, for example, what is the probability that theta is in between these two things? So let me, if we just put the theta outside here, what we're going to get at the end here is that if the interval z alpha over 2 multiplied by the standard error theta hat. So if as you can see, if you put this, so actually it's really easy to do that here. Let me just directly do it in the equation here. So if this is that probability, I can just multiply standard error here and also put theta hat, put theta the other way around. So it's going to be like this. So so what I want to do is I want to just leave theta in one place. So considering these two equations, for example, one way to do that is theta hat minus this one times z alpha over 2. So yeah, let me directly write that here. Theta hat minus z alpha over 2 times the standard error of theta hat, and theta hat plus z alpha over 2 plus the standard error of theta hat. This probability, okay? This probability is also going to be 1 minus alpha. So the only thing I did was to leave theta in one place. So since this is going to be negative, so I multiplied both sides again by -1 to change the error, to change the less than or equal to signs. But this is basically simple mathematics. Just multiply, put them there, and multiply by -1, which is going to get you greater than for this part. But if you do the same thing for this part too, you will change the less than to greater than sign, which at the end is going to give you this. So look at this equation. The probability that theta is in this interval is 1 minus alpha. So we get ourselves, so this is what the confidence interval is. So this slide here shows how we can get by adding or subtracting the standard z value of alpha over 2 with the standard error of the theta hat. So you just need to, for example, go 1.69 standard errors to the left and 1.69 standard errors to the right of your estimator. You get the probability that the actual theta is in this interval is 0.95. Okay, so this derivation is important because at first you may think that the derivation comes from the fact that we assume that theta is at the center. We don't assume theta is at the center. We don't know where theta is. Theta can be when we build a confidence interval. Okay, when we build a confidence interval around theta hat, the actual theta can be anywhere. We don't know where the actual theta is. So each time we are building a confidence interval, this slide shows those different confidence intervals nicely. So these are confidence intervals that are built for the same parameter theta, but by using different samples. So as you can see here, theta head is here, and this is where actual theta is. Theta is not a random variable. It has a fixed position. It's something that we don't know, but it's fixed. Now, when we say that this interval contains theta with 0.595 probability, as you can see, theta is not at the center of this interval. But in this case, it's contained. It's to the left-hand side, it's contained. In this interval, it's to the right-hand side and it's contained. When we say this interval contains theta with 0.95 probability, which means that if we take 100 different samples and build confidence intervals with the alpha level 0.05, 95 of them are going to contain your theta. And maybe one of them, look at this confidence interval. It doesn't contain theta. So we actually, by saying that with this confidence interval, confidence level, theta is, this interval contains theta, there's a chance, there's 0.05 probability that the actual theta is not in your interval. Okay, and this all comes from this derivation that we did here. We first standardize our asymptotically normal estimator. After we standardize it, we have a normal distribution, standard normal variable. And if we just want to have 0.95% of this standard normal variable, we want to find the interval which contains 0.95 of that population of this standard normal variable. In other words, 0.025 should be on the left-hand side, 0.025 should be on the right-hand side. This is a symmetric distribution. So we find the z-values to accomplish that. This is our standard variable, and we see here is that the probability that theta is in this interval is equal to the same 0.95 we have figured out. Okay, this does not mean that theta is normal. This means that our estimator is asymptotically normal. All right. So, the algorithm that we're going to have to build confidence interval. So this is the generic methodology to construct confidence interval. We first find an unbiased estimator for theta, and we have to check whether it is asymptotically normal. Our estimator is asymptotically normal as n gets larger. We need to find the standard error of our estimator. If, for example, we know the samples are already coming from, if we know the standard deviation of the individual samples, for example, what I'm saying is that if, for example, your estimator is, for example, a summation of these terms, or it's like an average. So let's try to actually do that. Let's try to find the standard error for an average. So what is the standard deviation of this when our samples are coming from some distribution that we don't know? They may be coming from any distribution, but let's assume n is large. But if we know if the standard deviation of these individual items are given to us as sigma, okay? So the standard deviation of individual random variables are given to us as sigma. And our estimator here is the average. So let's see. So let's assume this is x bar, okay? Which in other words, we want to, we sum them up and we divide them by n. This is our, we are trying to estimate the mean, okay? So what is the standard error of a mean of a sample size n? If the standard deviation of these are given to us, we can actually use the linearity of expectation Okay, so the summation, which is going to be equal to, since the variance is the, so in other words, we already know that uh, this is going to be equal to this, right? Because here, so let me actually write it like this. It's going to be the standard deviation of x1, xn divided by n. This is what our estimator is. What is the standard deviation of this thing? We are wondering about this. If these individual ones are this is given to us as some value, the sigma is given to us. What by using linearity of expectation, we know that the variance of these individual things, or the standard deviation of a summation of these variables is, or if you look at the variance, so variance of x1, xn, if each of them have a variance of sigma square, we know that it's equal to n times sigma square, right? So this is the variance of uh, summation of these so the variance of summation of n random variables is n sigma square. So we can actually take a look at that if they're all independent from each other. And since our samples are selected, data points are selected from the population in an unbiased manner, we randomly sample them. Therefore, they are going to be independent from each other. Let me just show you here. We always refer to what we have at the end of in the middle of actually chapter 3. Yeah, look at this table. So this table 3.7 is really important, uh, which tells you that if you have these variables, for example, in particular, what we have here is that if we have these things, for example, for independent x and y, variance of x plus y is equal to variance of x plus variance of y. Variance of y. So if we have n of these variables which are independent from each other, it's going to be n times the variance of x. If variance of x is sigma square, it's going to be, so this last equation that you see here is used here to find the variance as n times sigma square. So it's a summation of n sigma squares. Therefore, the standard deviation of this sum, so the standard deviation of this sum, if you take the square root of this thing, it's going to be square root sigma, right? If you take the square roots. Therefore, it's going to be square root of n sigma divided by n. And since this is a constant number here, when we have, that's another thing that we are using. If you have a constant number that is here, that constant number is squared, its variance. So the variance of this thing is going to be 1 over n squared. 1 over n, so this is going to be, if you have another n here at the beginning of all these things, it's going to be 1 over n squared here, but when you take its square root to find the standard deviation, what you're going to get at the end is this. So the standard error of standard error of the average of your sample is equal to this thing, which is equal to this, right? I mean, square root of n divided by n simply means sigma divided by square root of n. So this formula here, you're going to face this a lot, okay? Which tells you the averages, because we are going to be doing things about we are going to estimate population mean, and in that case, our estimator is going to be x bar. So if you have a sample of size n, its standard deviation is the standard deviation of the individual variables divided by square root of n. So there are nice implications here. The square root of the summation is actually the standard deviation. All the summation itself increases by square root of n, because each individual element has a standard deviation of sigma. If you look at the sum is going to contain more errors, right? Sum contains more errors. If you just look at the sum, it's a buildup of errors. Therefore, the standard deviation of the sum increases as n increases. But if you look at the average, on the other hand, the standard deviation of the average decreases because this the standard deviation of the average. The average has this 1 over n term. Therefore, we by using linearity of expectation, we have the variance 1 over n squared. So the standard deviation of the average, on the other hand, has this divided by n term, which tells you that average, the standard, if you look at the average of multiple things, as the sample size increases, that standard deviation decreases by square root of n. All right, so if you again need, if you want to reduce the standard error by half, you want to quadruple, you want to multiply your sample size by 4. So this is what it's saying. So this is really an important part because I emphasize this. We will be using this a lot in our confidence level building, confidence interval building, and also in hypothesis testing. We will be using this a lot. But this is one thing that we did. If we know this sigma, what if this sigma is unknown? We are going to see cases like that. We are going to see different cases where let's see, let me write it here. Okay. If we have a large sample, there are two cases. Large sample. When we have a large sample, if our estimator is asymptotically normal, and there are two cases here again, a known standard deviation, unknown standard deviation. So what does this mean, known and unknown? It means that somebody gives you already, when we have these individual samples, somebody may tell you that the variance of these individual variables in the population is this value over, for example, in the last 100 years, we have may observe this, and this is given to you. Okay, in that case, the standard deviation of the individual data points may be known, and or it may be unknown. In the case that is unknown, we are going to estimate this standard deviation with S. The sample variance, we will be using sample variance for those individual items to estimate. We are going to use our estimate for sigma when we have unknown sigma. Okay. When we have large samples, the good thing is that our estimator is asymptotically normal. We need to also have an asymptotically normal estimator. So we are going to have large samples, unknown standard deviation, known standard deviation. We are going to see these two cases. Another case is that we may have a small sample. Okay. When we have a small sample, we may not think about the asymptotic normal anymore because our estimator may not behave normally as a normal distribution. But here, in the case that the small sample, the data points are not known to be normally distributed, we are not going to see any techniques. There are some complicated, difficult techniques in that case, but we are going to assume normal at this point. In this course, we are going to see the case where we are going to assume that they are normally distributed. And when we have the known standard, known sigma, let me also write this one at the bottom to be consistent. When we have known sigma, we will still be using, if the individual, assume normal for xi's. Okay, if we know that individual data points are normally distributed, even if we have a small sample with known sigma, we will be able to compute these things. We will be able to compute normal distribution. We will still be using the z table, the standard normal table to that. Now, this fourth example, when we have small samples, but with unknown standard deviation, you're having small samples and we don't know how variable our samples are, our data points are, okay? In that case, you're going to see a new distribution, which we call the students t distribution. Students t. And we're going to use a different table, a students t table, which is, if this is, for example, a normal distribution, student t is going to look something like this. Okay, so this one is t, and this is z, the other one is z. As you can see, it's going to assume more errors. So if you want to build the same confidence interval, for example, 95% of the area under the curve is in this interval. In order to get the 95% of the area uh, under the curve for the red one, your interval has to be enlarged, because since with less information than the student's t, we don't know the actual variance, so we will have to estimate our standard error by using the sample standard deviation. In that case, we may be making more errors. Therefore, if we don't know the individual standard deviations of the data points, and we have a small sample, we are going to be using a different distribution for that case. And this one comes from this practical problem of quality control in brewing, the Guinness brewery. So William Gossett was the person who came up with the student's t distribution. Okay, so I always thought the student's t was something about students. Actually, student was the pseudonym of William Gossett. So he used the, I think, in brewing or Guinness at that time, they did not allow their employees to publish papers by using their names, because this is there's competition among different companies. They are like company secrets, these things. So I think they had to stay anonymous, and he was using the pseudonym of student, and that's why it's called student's t distribution. But it was William Gossett who came up with this while he was trying to figure out the variation and trying to make quality Guinness beer. Okay, so these are the four cases we are going to see in the remainder of this chapter. All right, now let's continue with our slides. So here's the generic method that we have. By the way, this z, as I said, is going to be replaced by the t table if we have a small sample with unknown standard deviation. But still, we have to know that they're coming from normal. If they're not coming from normal, so this generic method, when we have an estimator that is normal distribution, then we can use this z, d values. We compute the standard error of the estimator depending on whether the individual standard deviation is known or not. We'll have to compute this part differently. So this part is going to differ in different cases for known standard deviation and unknown standard deviation. So we find the standard error. We obtain these plus minus z alpha over 2 quantiles from the standard normal table. And there are some well-known values. Let me go to the book again quickly, chapter 9. So here are some most widely used values of that z quantile values. So right here. Yeah, for example, z 0.025 is 1.96. So if you want to have an alpha value of 0.05 or with 0.95 confidence, you have to go 1.96 standard errors to the left and 1.96 standard errors to the right of your estimator. This is what it's saying. If you want to decrease your confidence, okay, let's decrease our confidence to 90%. Or 0.90, with 0.90 confidence, instead of going 1.96 standard errors, you can actually go 1.64 standard errors to the left and to the right of your theta hat. This will obviously decrease the interval size. As you can see, it's a smaller z-value. You're going less standard errors. If that standard error is fixed, your sigma is going to, I mean, your margin is going to be smaller in this case, but with, as you can see, decreased confidence. You can even decrease your confidence even more if you want to have 0.80 confidence. Okay, 0.80 confidence. You can go 1.28 standard deviations to the left and standard errors to the left and to the right of your theta hat. As you can see, if you want to have more and more confidence, how that interval changes. You either, another thing is you can decrease your standard error by increasing your sample size. That's another thing. I mean, this may remain the same with the same confidence level, 1.96. But if you decrease your since you multiply this with your standard error, if you decrease your standard error, this one is called the margin, as you can see. This will, if you decrease standard error, margin is going to be decreased, which will result in a smaller interval. All right, so this is in the general method here, which is also written here. We just go this much standard error to the left and to the right of our estimator. So let's start with population means. As I said, we are just going to talk about population mean, difference between population means, population proportion. So here is our estimator. This is our sigma. We already did that part. Okay, we already have found what is the standard error of x bar, sigma over square root of n. So how did this formula came about? By using the linearity of expectation right here. Okay, this one is a theta hat is sum of variables divided by n. So which is going to be equal to 1 over n square root of n sigma, and then we came with this formula. Okay, so in other words, if the sample comes from normal distribution, then the estimator is also normal, independent of the actually sample size. Okay, if your even if your sample size is small, if it's coming from normal distribution, the estimator is also normal. If the individual variables are not coming from a normal distribution, our estimator is going to be normal if sample size is large. Okay, so this, the second sentence says that if the sample comes from any distribution, x bar will be normally distributed if n is large because of central limit theorem. As you see, we are applying the things we have learned in chapter 4, chapter 3, linearity of expectation in chapter 3, the central limit theorem in chapter 4. So everything is connected to each other. So here it's an unbiased estimator. This is a standard error. So if you want to have a population confidence interval for the population mean, x bar is your estimator. Go this much standard deviation standard errors to the left of x bar and to the right of x bar. This will be, for example, if alpha is 0.05, 95% confidence interval for your mean. So let's take a look at example, and I will stop after that point, and we're going to continue with confidence intervals next week, and probably we'll finish and start hypothesis testing, which is very similar to, which is just a very natural extension of confidence intervals. We will again have the same alpha in our hypothesis test. The alpha will be that we use is going to be the same. But let's take a look at this example, and we are going to continue with the confidence interval for the difference between two means next Tuesday. Okay, we'll finish with this example 9.13. So let's right here 9.13. So construct a 95% confidence interval for the population mean based on a sample of measurements. If measurements have normal distribution, measurement errors have normal distribution, and the measurement device guarantees a standard deviation of sigma is equal to 2.2. So this example is good in the sense that, so you may be wondering, how do we know the population sigma? Sometimes this comes from, for example, you may be measuring certain things. For example, you may have a laser distance calculator, and you're calculating distance to some point with your laser distance calculator. Sometimes the manufacturer tells you that the actual distance is computed with this error. The error in the measurement device is your standard deviation most of the time, and it's provided to you when you buy that measurement device. All right, so this is these plus minus things, or the standard deviation is given to us by the thing that we buy. So the measurement errors have normal distribution. Measurement device guarantees a standard deviation. So we are going to compute. The sample has size 6. Sample mean is this one. To attain a confidence level of 0.095, we already know that it's 1.96, right? So this quartile that we know, 1.96 was one of those widely used Z quantile values. So since this 2.2 is known, we need to go. So what is the standard error of the average? It's 2.2 divided by square root of 6. So 2 divided by square root of 6 is the standard error. So we go 196 standard error to the left and right of this 6.5 that we obtain as our estimator, and it becomes 474 and 826. These two values, okay? So this tells you that the actual, if you have the sample, the actual population mean is contained in this interval with 0.95 probability. Okay, so that's it. So when the sample size is small and the distribution of data is not normal, we will not be able to apply this method. Okay, we will not be also apply t distribution either. Which table? We use the standard table. So this is the so this one is also standard normal. So we always here it comes from this GIMP slide. Let me just show you again. Where do I have it? Yeah, right here. So this one, by showing that our estimator is asymptotically normal, or for a large n, we always use the standard normal table. Okay, to get those quantile values. It's the Z table that we use. The Z is the standard normal table. All right, but in the exam when we ask these questions, we will be using one of these well-known Z values that are written here. I mean, these 1, 2, 3, 4, 5, 6, these 6 of them, you encountered them a lot. So we will be using one of these values. When alpha is 0.05, it's this. When alpha is 0.1, it's this one. When alpha is, for example, equal to 0.02, but if you want to get, for example, 98% confidence, if you want to be 98% confidence, this is going to be your Z value. If you want to be 99% confident, this is going to be your Z value. And these will be the standard ones. So all of them, all these quantiles, they come from the standard normal table. All right, I hope it's clear. Yeah, that's it for today. I will stop recording now. We will continue with standard estimation between population means on Tuesday.